This is the second to last lesson of our search and sort algorithms in JavaScript module. And then we have a few other lessons under a title called Days as a Developer, sort of general developer knowledge. So that is it. I hope you all are feeling, I'm sure, excited to be at the end, but also hopefully feeling good about all the hard work that you all have been getting up to. All right, we can jump into merge sort today. So remember yesterday we talked about recursion. Today we'll be talking about yet another sorting algorithm, this time using recursion. And so we will see what that looks like. As a reminder, again, the important thing here is for us to be practicing our skills with problem solving, thinking through pseudocoding, all that kind of stuff. We'll get plenty of practice with that today. All right, there we go. Screen shared. Fantastic. All right, so we've talked about a number of different sorting algorithms, right? We talked about bubble sort, we talked about selection sort, we talked about insertion sort. Today we're going to be talking about merge sort. Next time we'll be talking about quicksort. These two sorting algorithms are a bit more efficient than the other sorting algorithms we've learned about, and we'll see sort of why that is. We can think of it kind of like they are merging a bit of the best parts of our searching algorithms as well as the benefits of like binary search and splitting data structures apart. So we'll see that's a little bit more performant than some of the other ones. Today we're going to cover merge sort. So in this lesson, we're going to explore merge sort, an efficient, stable, and comparison-based sorting algorithm. You'll learn about its divide and conquer approach and implementation. By the end of this lesson, we're hopeful that you will be able to implement merge sort in JavaScript and analyze the efficiency of merge sort. So that is the goal. All right, on this page, we can see a bit of a GIF here highlighting merge sort. It's a little hard to, I don't know, 100% understand kind of what's going on here. And so we'll watch a video and some other examples a little bit later. But the main idea of merge sort is that we are taking our list, we're splitting it in half, and then we continually do that, right? We keep breaking everything in half and half and half and half and half. So you can imagine this might be sort of a recursive part of our function. And then as we get to the smaller list of just like one item, two items, we start to merge those lists together into a sorted array. Those sorted arrays then get returned, and that works up to the next step, where the sorted arrays on either side then get merged with each other. We then take that merged array, take it up to the next step, and so on and so forth. So what you can see in this GIF right here, what it's trying to show is these different chunks of this data set getting sorted together into larger and larger chunks. And so as we can see, like right now in this big one, we've separated it from multiple tiny little lists into two big lists. And then it goes ahead and sorts all of the values together into a big sorted list. So again, let's see a few more examples of this, but it's a pretty clever solution. And there's really, I would say two different steps to it, although it has here this list of three. So the different list items here. So what we do with merge sort is we'll split the list into two halves. We then have the conquer step where we recursively sort each half. And the way we do that sorting is by combining or merging the two halves to produce a sorted list. So I would say really two steps. One overall process is about splitting our selection into halves and recursively calling merge sort. And then the latter half is us merging together arrays so that there's a resulting array that has all the items sorted. So two kind of big chunks or steps that we'll be walking through today. All right, so how is merge sort different? So unlike some of the other sorts we've worked on, which have an average and worst case time complexity of O of n squared. So remember that was the quadratic version where the graph went up like this. Merge sort performs well in large data sets with a time complexity of, and this is be a little confusing here, but it's a big O of n times log n in all cases. So if you all, I guess I don't have the graph up. I should have done that. Let's see if big O cheat sheet, so we can just try and look at this. Just want to show the graph here. Again, we saw this when we were talking about algorithmic complexity. So O of n squared, that's this line right here. And this graph seems so opinionated, right? Horrible, just absolutely horrible. It kind of depends. On very large lists, this will end up taking a long time, right? So that's O of n squared. That's the three previous sorting algorithms that we found. Merge sort falls in this kind of middle ground, which it says is bad, but is pretty good as far as sorting algorithms are concerned, of n times log n. So do you all remember we worked with an algorithm that was log n, or we talked about that. Any idea what that was that we discussed that had the measurement of log n, not n log n, but just log n? I know I'm asking you to go back. What do you all think? Was there any algorithms we talked about that had an efficiency of O of log n, like we can see down here? All right, how about I scroll down this way? Any of these seem there's no like search specifically in here, but that's okay. So if you'll remember, when we were talking about binary search, right? The idea was that was quite performant because everything was sorted. We were cutting everything in half, right? We were cutting the collections in half. And that led to a situation where over time, the larger data set, binary search is actually great at it because it reduces the amount of operations that need to occur significantly. So on a small set of data, we talked about this with linear search versus binary search, the number of operations isn't really that different. If you had a list of 10 items, it's going to be maybe a bit more performant, but it's not really making that big of a difference. But with 10 million items, it's going to make a big difference. It's going to be cutting down the steps according to log n. That is the measurement of it. So n log n is a little bit worse. It's still in the bad comparison here, but it is much more performant than O of n squared. And so what this and Quicksort, which we'll talk about later, is going to do is going to, again, bring in some of the best processes from binary search and combine them with an iterative process that's going to iterate through and make a few changes as well. So that is the measurement for merge sort, which is n log n. Again, this doesn't necessarily have to do with the fact that it is recursive, although I think as we'll see, it does clean up the code quite nicely. It makes it much more understandable. So the recursive approach is helpful here, but again, has more to do with the divide and conquer strategy in terms of this measurement. It says down here for stability in space, we haven't really talked too much about space complexity just because it doesn't come up quite as much, and we didn't really talk about it too much initially in that first lesson. But in general, the idea is that you're trading off a little bit of efficiency with time, as opposed to and creating a little bit more space and using a little bit more memory, which is usually not too bad of a trade-off. All right, excellent. We have our video now. We'll go ahead and watch this. If you cannot hear or can't hear, please let me know in chat so I can go ahead and see.
Today we're going to learn merge sort. A few quick points, then we'll get to the example. Merge sort is usually done recursively. When you think of merge sort, as with other recursive algorithms, I want you to think of divide and conquer. We're going to break our problem into smaller problems in order to solve it. Let's get started. We have the following array and we want it sorted. We're going to continuously split the array in half, our divide step, until we are left with the individual items. Watch and see. Our array is now broken down into individual items. One note before we start sorting. When you implement this in code, these steps will be done in a different order because of recursion. But I think this human-friendly order provides more clarity in learning. Let's continue. We're ready to sort. We'll examine the individual items, compare their values, and merge them into temporary arrays. The temporary arrays are sorted, but there's work left to do. Let's jump up the recursion stack and continue. We merge our smaller arrays into a larger one, inserting items in the correct order. One more merge, and we'll have our sorted array. And that's it. Our array is now sorted. Here's the pseudocode for merge sort. On the left you have the recursive part, which halves the arrays. On the right is the merge function, which combines the arrays. Merge sort has a worst case time complexity of big O of n times log n. The easiest way to think about it is to start with the merge step. Looking at the while loop, we see we have to visit n items. The log n comes from the maximum height of a binary tree we create, which is on the order of log n. Thank you for watching. Please comment suggestions for future videos below, as well as any
Got to mute. All right. Hey, y'all. Excellent. I see a few comments in. Welcome back, those of you who are struggling with internet. Apologies about that. So we're covering merge sort. So in that video, just notice a few things here that we can, this person described and that I would say was nicely illustrated here. We're breaking down the array into individual little parts, right? So we're just doing one by one by one by one by one. At that point, an array, or yeah, a list of one item is sorted, right? So then we're taking two lists, and then the process we were following, right, of filling in those values was to go through each list and sort of figure out, okay, what number needs to go first. And so, for example, in this example, we looked at the two lists and took one, that went first, then four, that went next, then seven, that went next, and then nine. So this is sort of that second step I was talking about of we have to merge these arrays together. If you're merging arrays of just one item, right, we're just doing maybe one comparison between. Otherwise, we're having to compare multiple items to one another. And the first step that we saw up here was the divide part, right? That's us splitting apart everything. So we'll see this more with code, but just wanted to show you this. And as you can see, this code is a little bit more complicated than before. Again, this is the merge sort function itself. If we could just say our algorithms, we wouldn't have to worry maybe too much about merge. We could just say merge these two, right? Maybe you would figure it out. But this is sort of the main idea here is let's split apart our array and then call merge sort. And then once the length, the size of these arrays is equal to 1, then we go ahead and merge these together. All right, let's take a look at a visual example here like we've done before. So we have here an array of 43926. The first thing you're going to do is go ahead and split those arrays into equal parts as best as you can. You keep doing that until it reaches one element, and that's your base case for this recursive function, right? Once a list has just one item, it is indeed sorted. Once those items are sorted, then the function will return its base case, and so they move back up to the next step. And so once we hit our first pass through, in terms of powers for thinking about merging things will be an individual item in an array merged with another individual item in an array. At that point, we'll need some sort of algorithm to decide, okay, which one's less than the other. Let me place that in the right spot and then add the next value. That process just continues all the way up. So we continue to merge values across the board on the furthest level down in the recursive stack. And then moving up, we start to merge these values upwards as well. So you can see here we're merging the 4 and 3 to 3, 4. We're merging these smaller lists where 2, 6, and 9 are coming together. And then you end up merging together everything so that it all goes into the completed list. It certainly, I think, it feels a little confusing at first because what the feeling I think of the algorithm is you'll split everything and then you merge all the way back up. So it feels like this big expansion of all these little tiny little arrays, and then you're doing smaller and smaller comparisons. Yeah. All right, so we discussed this in terms of time complexity and space complexity. Again, this is a bit more confusing, but is more efficient in terms of time complexity. All right, let's go and run through an example here so we can really make this solid. I'm going to do the same thing I've done before. I'll go up here to view. We'll go ahead and pick out, here's that file tree. I'll pick up, let's say pseudo.txt. Okay, so so we're going to go and practice with this array here and sort of just walk through the steps as a group for merge sort. So we have our list, which is, I guess I'll just copy this over here. Excellent. All right. And then what we're going to do first is we're going to split the list to all items until all subarrays, perhaps we'll say, are at a single length or less, I suppose. So what that's going to look like is the first split, right? We look at this as 1, 2, 3, 4, 5, 6, 7 items. So we could perhaps split here. We'll then split again. Let's split this one in half as well. And then we'll split again. This 38 can actually remain the same. So depending on how you want to sort of visualize this, we could say we could just leave this as is, or we could like put an empty array next to it. Just kind of depends how you want to think about it. So let's do this. I'll just to highlight that we're splitting multiple times, we'll just put like an empty array right here. So now we've ended up with this long list of single or single items or less, right? These arrays are all sorted now, that they have one or less items. At this point, then we start to merge these pairs together. So the first merge that's going to happen is with our empty array in 38. Pretty easy, right? We end up with that one sorted. Fantastic. With 27 and 43, we need to do a process where we compare 27 to 43. 27 is less than 43. So I'll go ahead and just join those together. We do the same thing with 3 and 9. 3 is less than 9, so we'll join those together. And then we have 82 and 10. 82 is not less than 10. So we'll go ahead and join those together, but swap the positions of them. Great. So we had all these very tiny arrays, and now we have still tiny arrays, but slightly larger. Now this next step, I think this is just important to really slowly walk through here. For 38, 27, and 43, so these are two different arrays, slightly different sizes. what we're going to do in terms of the process is we're going to look at the beginning of each array. We're not like thinking, okay, how do I put this in the middle of another array? We're just looking at the beginning of each of these arrays. So the first values we're comparing are 38 and 27. 27 is less than 38. So we make a new array or a new spot, and we're going to put 27 down there. We can think of this as like we've removed this from the list now, right? That right side, we're taking it and we're putting it into this new array, this subarray that just has the value 27. And then we're going to compare 38 and 43. 38 is less than 43, so it goes into this new spot right after 27. All right, we've moved that down. At this point, we don't have any values to compare in that left array. So what that means is everything in the other array is already sorted and is going to be larger than all of the values within that little subarray we've made. So we can take everything in the right array, which at this point is just 43, and we can add that to the very end. Let's do the same thing over here. It wants to add that period. So we have 3, 9, 10, and 82. So to make this little subarray, this is going to be our merge function. What are the first two numbers we're comparing with these two arrays? What are the first two numbers that we're comparing? There's no function for us that just says, hey, compare the entire array. So what are the first two numbers that we're comparing? And we got some folks typing. Give you all a sec here. All right, excellent. So a few different guesses here, right? And so we want to think this is our left array, this is our right array. So the first thing we're comparing is the first element of each array, right? So Joseph's got it. So we're comparing 3 and we're comparing 10. The first element of each of those arrays. Once we have that, we're going to see that 3 is less than 10, and so we'll move 3 down to here. The reason why this is important, why we're checking the first item of each array, is because those arrays are already sorted. So we should know that the first item is the smallest item. And so we're comparing between the two arrays, the two sorted arrays, the smallest items, and figuring out which one is smaller than the other, if any. So that's why it's important we need to check the first item of each array, not just one individual array. We'll see this a little bit clearer when we have a few more numbers here. So let's continue this process. So the next thing we'll do is we need to compare the first number of each of these two array. So what two numbers are we going to be comparing? I'm sure I feel like a broken record here, but what are the first numbers that we're comparing? Or sorry, what are the two numbers that we're comparing from these two arrays? Uh-oh, I spooked you all. It's not, don't overcomplicate it. Don't think too much about it. So we need to compare two numbers from these two arrays. What are the two numbers we're going to compare from these arrays? It's okay if you're wrong. I don't have a scorecard over here. Yeah, excellent. Thanks, sorry. Thanks, Joseph. So we're comparing the first elements of both those arrays. Why? Because those are still sorted. So we want to compare those smallest values. So we'll see 9 and we'll see 10. 9 is less than 10. Excellent. So we move 9 down to our little subarray. At this point, we have no items left in this left array of the two that we're comparing, right? We have no items left here. So what that means is we can just add all of the numbers from this right array to the end of the array that we're creating. The reason we can do that, again, is because we know those values are already sorted. We know we've already sorted them as part of our previous process. So all those values should be sorted and larger than all of the other numbers that we found. So we can just take 10 and 82 and we'll merge that down here. All right. And we're just comparing two numbers, right? It's all easy. And then we get to like more. It's like, oh, man, what's going on? What's happening? Let's do this one last time here. So we have one last step. So now we're creating our final sorted array. We have two arrays that we're comparing, just like we did all the way up here, right? So this is going to be the recursive step. We have two arrays that we're comparing. We're going to merge them together. Same question again. What are the two numbers we're going to be comparing first between these two arrays? What are the two numbers we're comparing first between these two arrays? All right, we're getting it. Thanks, sorry. Perfect. Okay, yeah, so the first numbers are the first elements of each of these arrays. We want to compare 27 and 3. 3 is less than 27, so we'll go ahead and move that down to our next array. The next two numbers we're comparing are the first elements of each array. So we compare 9 and 27. 9 is less than 27, so we move 9 down there. We'll move it from our array up here. The first numbers of our two arrays we compare again. That's going to be 10 and 27. 10 is less than 27. So we move that down here. And now we're left with 82 in this. We're going to compare the first elements of these two arrays. Again, I'm sure you're getting sick of me saying this, but I just want to make sure we're really clear on this. So we have 27 and 82. 27 is less than 82. And we can see if we keep following this process, all right, we'll compare 38 and 82. 38 is less than 82. We then have 43 and 82. 43 is less than 82. At that point, one of our arrays is empty, so we can just tack on the remaining array. And that's how we get to our sorted list. So the first thing we do is we split everything up, and then we take these individual little pairs and start to merge them together, one after another. And the process we follow for that merge step is we take a look at the two arrays, take a look at the first number of each of those two arrays, determine which one is less, put that into our new array that we're creating, and then do the same thing again. And just continue doing that until one of those arrays is empty, at which point we can just tack it on to the end. All right, I've talked a lot. Any questions on this? Any confusions? Anything feeling particularly uncertain? Anything lingering? All right, feeling okay? Cool. Yeah, totally fair, Tatiana. And great segue. Let's go ahead and practice a bit more. There's only this one check for understanding right here, but I think this is worth just trying on your own for a brief moment. So I'll go ahead and let's create a new list of numbers here. I'll add one in, and we'll have you all follow along individually, and then we'll walk through it. All right, so real quick, everyone shout out some numbers for me in chat. Pick a favorite number, tell me your age, maybe your birth year, maybe it's just a number you think looks cool. Something between 1 and 100. All right, we got 9, we got 99, we got 32. This is the easiest call out question I have today. What's a number? Let's get a couple more in here. Got 1950. All right. Let's see. How many we had 6 here? We got 79, 44. I like this. I like this. I'm gonna add 11 and we'll add Stoop. All right. I'll paste this in chat. So you all go ahead and copy this onto your same file over here, or if you just have a piece of paper handy, that is a totally fine way to do this as well. Honestly, it's probably a little bit easier than trying to type this out, just rewriting the numbers and all that. So whatever works for you. I'll give you all a few minutes. I'll throw a timer up here for 2 or 3 minutes. I just want you to walk through this process on your own of splitting in half, splitting in half, splitting in half, starting to merge them together, and really be intentional about the process. So don't just look at two lists and be like, great, here's the order. Think, okay, I need to compare the first items. Which one's less? Great, I add that here because that's the process our computer is going to follow, and that's the code we're going to be writing. All right, let me put up a timer here. I'll put up a timer for 3 minutes. We will come back in just a bit. All right, I hope you all have had a few minutes to be able to try this out on your own. If you're still finishing up, that's a-okay. Go ahead and just finish up. Uh, I'll go ahead and just get started here as well. Just try and type this out and we'll walk through this example. All right, so remember our first step is to begin by splitting up these lists. So we take our large list and we have, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 items. 1, 2, 3, 4, 5. So right here, right in the middle, try and visually make this a bit more clear. We can split up our first list once, right, into halves. Let's follow that same thing again. You have an uneven sized list. It's up to you sort of how you want to make the first one smaller or larger, it doesn't entirely matter. We'll do that same process again. Oh, it's getting too big. All right. And then we'll do that same process again. So at this point, it's a bit awkward because we have a bunch of arrays that are already just one size. So again, a couple ways to sort of visualize this. What I might do is something like this. I don't know. How do I type this out? This is where having like a whiteboard would be really helpful. Um, we'll do this. I'll just space these out like so. Uh, and we'll just note these are the first ones that'll have to get joined together. So we split everything out into its individual little component. Then we're going to start to walk through and compare all these different values to their neighbor, right? Once we have just one value, we're comparing. I should say compare and merge, right? That's the step that follows. So with 9 and 99, each of those is its own little array, right? Those arrays are sorted because they only have one item within them. So we check the first element of those arrays, which one is less. In this case, it's 9. So we take 9, put that down into our array. Our right side, which is an array of just 99, is all that we have left. We don't have any items left in the left array because we've moved 9 down. And so we add that array to the end of the smaller list. We'll do the same thing here. So in this case, we compare 32 and 31. 31 is less. That means everything is out of, we're done with that right array. So we add all the contents of the left array to the very end. We'll do that for the next one as well. So here we're comparing 19 and 50. We see 19 is less, add all the contents of the remaining array. So we end up with 19 and 50. We're going to compare 44 and 79. Compare those two, end up with a smaller list of 44 and 79. Same thing with 11 and 62. Those are already basically in the right order. We compare the first element of each of those individual arrays. See that 11 is less, add it to our new array, and then I'll add all the contents of the remaining array. So you can kind of see visually here, we're splitting up, right? Everything's getting spread out. And now we're starting to merge back together. So we'll follow the same step now with our additional arrays. So what we can do here is we can compare some of these values. How do I want to draw this? Do that. Put that over here for now. So we're going to compare 9 and 31 first. We see that 9 is less, right? So we're removing that from our array. We then check 31 and 99. 31 is less. We then check 32 and 99. 32 is less. And then we check 99. So that is our sorted version. Now where we have these like 3 remaining, this is where, again, our algorithm will handle this. Just a little bit hard to type out here. We'll just leave this last array at the very end as is, and then we'll merge it together. We have to do this kind of in a little bit of an uneven step right here. But we'll take these next few 2 arrays of 19 and 50 and 44 and 79. We compare 19 and 44. 19 is less. We compare 50 and 44. 44 is less. We compare 50 and 79. 50 is less. we add on the rest here. And so on and so forth. So this last couple steps, we can sort of merge in either direction here. Let's merge this right side first. So we'll compare this longer array with the shorter array. We're going to do 11 first, then 19, then 44, then 50, then 62. Then we'll add the remainders from the left side. And now we can merge everything together into one. So we're comparing 9 and 11, 11 and 31, 31 and 19, 31 and 44, 32 and 44, 99 and 44, 50 and 99, 62 and 99, 79, 99, and then we add 99 on there. So break up, bring back together. That is merge sort. Any last questions or thoughts here before we move on? Perhaps this was very repetitive. I apologize for like, yeah, I get it. I just want to make sure we have a record of all the steps. It's explained as much as possible. Any lingering questions here? All right, Tatiana seems good. Great, happy to see. All right, let's move on then to our pseudocode step. So I'll clear out my text here. So next step is for you all to write some pseudocode as we've done before. Here's the list that we'll start with. And there's some guidelines here. I'll put up a little bit of time here so you have a few minutes to get started on this and really try and work it out. The thing I'll say is there's really two steps here, right? So there's our first process, I think that's a better way to put it, is the merge sort process. And that is what we've just been talking about, sort of breaking everything up, bringing it all back together. The second process is this merge process. And this doesn't mean you have to have two sets of pseudocode necessarily. But I just want you to think about these two things as a little bit different. So maybe we could say this is the sorting part. And it's kind of the algorithm part, process part, something like that. Sorting part. I don't know. It's the overall process. And then there's a specific merge functionality, which is you have two arrays of sorted items. How do you merge them together? In terms of writing out the pseudocode, this might be the easiest thing to start with. Just think about, okay, I need to have some kind of functionality that given two sorted arrays follows a process to put those sorted arrays into a larger array. That might be an easier process to start with. And then thinking, okay, how does that fit in to this overall algorithm? Just a suggestion. You can do whatever you want. But I think it might be easier to start from there. So let me put up some time on the board. We'll give you a little bit of time to write through this. Write out the process that we've discussed here in class using your own words. You might want to walk through the example again here, make sure you're able to follow it, and then we'll come back together and discuss. All right, passing it over to you and put 5 minutes up. If you all are done, maybe give me a thumbs up or something in live chat. If you need more time, I will check in at the very end. All right, that's our time, y'all. Do folks need more time? Folks feeling good? You're able to walk through pseudocode? Let me know in chat. Guessing the silence is a couple more minutes then. I'm guessing they're just busy, so we'll give you all a couple more minutes. All right, hopefully the extra time helped out. I'm gonna go ahead and walk through the solution now that they have as part of this lesson. I think this is a pretty good example of what y'all could do. And then let me know if you have any questions as we get to the end of it. So they've sort of merged here the idea of a little bit of JavaScript, kind of syntax, a little bit of pseudocode, but I do appreciate the distinction here. So the merge sort functionality, the overall algorithm, process they're declaring here is if the list has one item or is empty, return the list as it is, which is already sorted. So remember, this is going to be our base case that we're setting up right at the beginning of the function. Otherwise, we're going to divide the list into two halves, and then we're going to, on each of those halves, call merge sort again. In the left half, we're going to merge sort with the first half of the list, and the right half, we're merge sorting with the second half of the list. So remember how it works with recursion, where as soon as you recur, this execution of the function stops until we get to some particular part of the step. So you can imagine as soon as we hit merge sort here, we're having until we hit this base case, in which case that gets returned, and then we move back up. At the end of this process, once we've uh, split everything into the right half and left half, once those are finished, we then merge the left half and the right half. And this merge function is what's down here. But that's the idea, right? We're splitting everything up. Once it's split up so that the values we're getting back are these first time through, either an array with one item or it's empty, then we merge, that gets returned back, and so on and so forth. It'll merge its way back up. The merge functionality, it has a left half and a right half. And what it does is it first creates an empty list to hold the merged list. And while both halves have elements, if the first element of the left half is less than or equal to the first element of the right half, that's our comparison of those two elements. If left is less than or equal to, we'll move the left half into the merge list. So actually move that element, remove it, and then add it. Otherwise, we'll go ahead and move the first element of the right half into the merge list, right? Because that means that the first element of the right half is greater than, or is less than, excuse me, than the left half. So depending on which one's less, that's the element that we move into our new merge list. Once one of those lists is empty, we just need to append, add on the remaining elements of the other half to the merged list, because those numbers are all going to be greater than every other number beforehand. Then we return the merged list. So there's a couple assumptions that I just want to be really hyper clear on here that I think you have to kind of make to best understand this. And when you're reading through, when we're talking through the merge portion, right, when you're looking through this part of our pseudocode, I think it's helpful just to sort of assume, great, merge is going to work. It works as is and merges those values. That makes it a little bit easier to think through this overall algorithm. And I think this is the right way to sort of think of the algorithm as we return early if the item if the array has one item or is empty. Otherwise, we're recursively calling this function, and then we merge at the very end. For the merge function, I think the big idea is that with these lists, we're always comparing the first element of each of those items and then moving those into a new array. There are some ways you can do this where you're don't have to make any modifications to the array, but I think it's actually easier to think of in terms of we pluck one value out of one array and push it into that new sorted list. At the very end, we're going to return everything, and then we're good to go. Any questions on this or any parts that feel a little confusing? If not, that's okay. It just means I've explained it perfectly. I'll take that as a compliment. That's what you all were thinking, right? Is that excellent. Excellent, excellent. All right, cool. So we have our pseudocode. I'm going to go ahead and copy this because our next step is going to be to write out this function. Oh, we're just too confused to respond. Oh no. Okay, well, hopefully the pseudocode is helping. If there's something specific confusing, let me know more. I'm going to copy over the pseudocode, and now we're getting to the implementation step here. You know, excited? Let's just implement it. Easy peasy, right? So I'm going to copy over the pseudocode just so we have it here in our list. And I'm going to try and help us sort of step through this a bit more slowly so we can build this out sort of step by step. First of all, thinking of our pseudocode, there's a few sort of functionality pieces here that you might want to just kind of think about and make sure we understand how to write using code. So the first one, we've already done this a few different times, but how can we divide a list into two halves? How do we split a list? And maybe actually the first question is, how do we get the middle of a list? How do we figure out that middle point? So let's say I have some array. I'll plug in our array that we created together. So what JavaScript can I use to find the middle point of this list? What JavaScript can I use to find the middle point of this list? What do you all think? We did this with binary search for sure. Trying to think if we did this with anything else. Maybe not. Definitely binary search. How do we find the middle point? What do y'all think? Finding the middle point of an array. Yeah, excellent. Thanks, Joseph. So we can call the array length and divide by 2. That should give us, oops, that should give us the midpoint. However, the array length could be odd as well, in which case we'd end up with like an array length of like 4.5 or something. So how do we make sure we get a whole number here? Because indexes are not at decimal points. We need a whole number here. So what code can we use to round up or round down consistently? Yeah, excellent. Thanks. Sorry. So we can use math.floor, and that will go ahead and give us the midpoint. And if we need to round down, we can round down. So let's just check our code here. I'll go ahead and just say console log mid, and we can take a look. Great. So that's getting us a middle point of our array. Fantastic. Now, if I wanted to split an array, I wanted to create a new smaller array based on some larger array, how would I do that? What are some JavaScript methods I might use? Uh, yeah, well, in what ways can I split a list into two, or split a part of a list off? Yeah, excellent. Sorry, yeah, right. So we can use slice. So slice is a method. I'll go ahead and just test it or show you all over here how it works. Let's plug in our array here. So I'm just now in nodes. I'm just running some JavaScript on the side over here. So you have this array, fantastic. So the slice method takes a number of different arguments. If no arguments are passed in, it returns a shallow copy of the array. I definitely remember us talking about this. I think it was just like months ago, perhaps, right? It says returns a shallow copy of the array. If we put in one argument, let's say I put in here 3, what's happening here? So what is the first argument in slice? If I pass in a number, what's the first argument in slice doing? How would you describe this? All right, so Joseph's suggesting, is this like maybe the length? Well, it has changed the length for sure, but we can see the anticipated array here is longer than 3 items. Sorry says the start point, and yeah, so I think that is on par there. So this is the starting index from which this new array will begin. So we take a look at our original array, 0, 1, 2, 3. At index 3 is the number 31. If we array.slice, pass in 3, that's where our array is going to begin, at index 3. If we include a second argument, you'll see we end up with something different. So what is given this? So the first argument that gets passed into slice is the starting index at which we'll begin slicing out part of the array. What's this second index? What's the role of this second index? What do you all think? What's the role of this second index? Remember, we have the original array right up here. So the first index was the starting index. Yeah, thanks. Sorry. So end index or end point. One thing to note here is that it's the first argument is inclusive of the index, while the second argument is exclusive of the index. So what I mean by that is here we're saying array.slice 3, 5. So we look at our original array, 0, 1, 2, 3, right? 31 is at index 3. 4, 5. At index 5 is 50, but notice 50 is not included within this point, right? It's not included within this point or in this array. We just get 31 and 19. So the first argument is the index at which to start slicing, inclusive of that number, inclusive of that value, I should say. The second argument is the index at which to stop slicing, exclusive of that value. So not including it. Certainly a little confusing, but actually works nicely as we'll see in terms of like this particular situation. All right, so that's array.slice. So we have array.slice as our way of splitting arrays. So what I want to know now is how do I make an array? I guess how do I split this array? That's what I want to know. We have the midpoint, right? We have the midpoint of the array, and now I want to split this array into two separate arrays. So let's start with the one on the left. How do I create an array using this midpoint that will grab just the numbers 9, 99, 32, 31, and 19? I only want to grab those numbers. I want to cut the array in half, right? What code can I write given mid, given array.slice to achieve that goal? See some folks typing. Give you all a second to think about it. All right, so let's go ahead and try, sorry, suggestion here, which I like. So if we say array.slice 0, so that's the start of the array, and then we would put in mid, right? In this case, we know mid is going to be 5, so I'm just going to put in 5 here. You can see that does indeed grab the first part of the list. So nice job. So I'm just going to define mid as 5 here so we can look at the exact code. So from 0 to mid, that'll grab the first part. How about grabbing the second part of the array? How do I grab the second part of the array based on what we've seen here? Yeah, Sorry's on it, on fire. Right, so now we can say array.slice mid. This actually works to our advantage, sort of strange nature of dot slice, where the first value is inclusive and the second value is exclusive, because we can just use this same value here. So when we array.slice from mid, we'll grab everything in the second half of the array, we say 0 to mid, we'll grab everything from the first half of the array. All right, nice. Getting good. Was there anything else down here? Yes, there's one more thing. Um, so last bit I just want to talk about in terms of like some code, again, some techniques we can use uh, to best build this algorithm. In the merge functionality down here, we have this part where we want to move the first element of the left half, that is like that first array, to the merged list. So the question here is like, how do we remove an item from the beginning of an array? And how do we add that removed item to the end of a new array? So for example, if I had two values here, I'm going to say left example, we'll say 1, 4, const right example, and I'll say 9, 20. In this new array, we want some way to, we're going to compare these values, right? But for example, how do I remove an element that's the first item in an array? What method can we use to remove an item from the first position of the array? What array method? We learned a number of them back when we were first talking about arrays. So what method can remove an element from the beginning of an array? All right, I see some suggestions here of pop. All right, so let's go ahead and I'll put in, oh gosh, code is getting slow on me. Oh no, what's happened? Uh-oh. Okay, there we go. I don't know what's going on. All right, so we have our left example array. So if I say left example dot pop, so this says 4. What's 4 mean? So the return value of left example dot pop is 4. Why is that? Right, just it says that's the last element. Sure. Yeah. So pop, remember, removes elements from the very end. So if you look at left example now, we removed the wrong one, right? We removed the one at the very end. That's okay. We can add things to the end of an array with push, right? So we're back to where we were at. If we want to remove something from the beginning of an array, we can use shift. So to pull something from the beginning of an array, we'll use the shift method. This method returns that item. So if we wanted to remove the first item from one array and add it to the end of a new array, what it might look like is something like new array dot push left example dot shift. You can break this up too, right? So we could break it up as something like removed equals this, and then we push that value within. That's going to allow us to remove something from the beginning of an array, and then we add it to the end of another array. All right. Whew. That's a lot. So we walked through a few of the techniques I think you might all need to use here. A lot of the other ones I think should hopefully feel pretty straightforward. I mean, when we see something like if else, we're probably going to use one of our conditional statements. We see something like while or for every item, right? We're probably going to use that iterative loop. We see something about returning, we're probably returning, right? So there's going to be a few different conditions you are going to have to build together. I'm going to say let's first spend a bit of time just writing the merge function. So we're just going to write the merge function. We're going to ignore merge sort right now. Instead, just write the merge function. So to get started with that, what you could do is write a merge function. We have our left and right arrays. And then let's go ahead and I'll console log here, merge. These arrays, our assumption is that they are sorted already, right? So that is an important thing to get in here. So I'll say like 2 and 8, 9 and 10. Oh, those are already sorted. Let me do something a little more complicated here. 3, 7. Sure, let's do that. So this code, when we run it, the result we're trying to look for is that we end up with a return value of 2, 3, 7, 8. So let's first work on a separate function called merge. That's job is to take two sorted arrays and merge them together into one array. You're probably going to be using this kind of code right here in some capacity. And the actual functionality is listed in, for example, the solution pseudocode. Or of course, if you wrote your own pseudocode, then you can follow along with that. So that's step one. I'll give you all a little bit of time to do that. Any questions on our first step here? So we're going to understand what we're doing, what we're trying to attempt here. We're going to merge these two arrays into one array that is sorted. All right. Let's give it a shot. I'll put some time up. I'll switch back over to this page so that you all can continue to look at this code while we're walking through it. I'm gonna put 9 minutes up, but if you get to a spot where it's already working, please do let me know in chat. It's always kind of just a vibe check, trying to figure out the appropriate amount of time for these different things. So we're just working on the merge function right now. Got about 9 minutes. Go for it. All right, y'all, so that was about 8 or 9 minutes. Folks want more time for the merge function? If so, let me know in chat. If not, go ahead and share out whatever output you're getting from merge. All right, excellent. Sorry, so it's a little more time. Cool. I'll add a few more minutes on the clock. If you all are done, please do share the output to our live chat. I'll go ahead and add another 5 minutes here. All right, that was some extra time, folks. How was it? Difficult? Is it fun? I realized I probably could have shared more about this part of like appending the list, but you all actually have the tools to do that. But we can talk a bit more about that as well. How are folks feeling about this merge functionality? Anyone happen to get it done? Feel good about it? More says it was painful, but hey, it looks like it's working. So that's positive. Excellent, excellent. All right, well, let's walk through a solution here for merge. I'm gonna go out on a limb here. I think this is like the most difficult code to write is this merge function. And then I think the merge sort function, that's kind of the hardest conceptually to think about. That's kind of how I would think about this. So for the merge function, right, we are two lists. These lists should be sorted. That's the only way this will work. They must be sorted. But assuming those are sorted lists, then we can go ahead and build this out using our pseudocode. So the first thing we'll do is create an empty list to hold the merge list. Great, I can follow directions. Let's go ahead and do that. So I'll create a new array, empty array called merged. That is a variable. Now the next thing is while both halves have elements. Have elements. So for them to have an element, we have to think of how can we represent that with code. So I would say there's probably a couple ways to do this. We could say something like while left.length and right.length. This is us saying, so let me adjust this a little bit here. This is saying while the left array has elements and the right array has some elements. Okay. And now we want to say if the first element of left half is less than or equal to the first element of right half. So this is comparing those elements. So we can set up our conditional. We have this if statement, right? And we see there's an else here as well. So we know that's coming for us. So the first element of the left half is less than or equal to the first element of the right half. So I can say left at 0, that'll grab us the first element of the left half. That's less than or equal to the first element of the right half. Okay. If that's true, we want to move the first element of left half to the merged list. So we saw how to do that up here, right? We're going to remove the first element of one of the arrays and add that to the end of our merged list. So I can do that in one line by doing something like merged.push left.shift. So dot shift should remove that item. Push will add that item to the new array. Otherwise, that means that the right side is less than the left side. So we're going to do the same thing, but we're going to switch the array that we're shifting from. Okay, and that is that step right there. Excellent. So the last step here is once one half is empty, append the remaining elements of the other half to the merged list. Let me ask you all, how did you end up doing this? How did you end up doing this step? Or maybe just more generally, how can we merge two arrays? How can we merge two or more arrays, I guess I should say. What do you all think? Any ideas? I can think of two ways to do it. Yeah, sorry, adding question marks. But yeah, concat should work. Let's try that over here. Can I clear from here? Let's go ahead and clear this. And node. So I'll say our left is going to be 2 and 8. Our right is going to be 3 and 7. This isn't quite going to be exactly what we're doing right here, but let's just check out how we can use some of these methods. So concat will create a new array that joins together. It creates a new array with both items. The items from the array you're calling it, the method on, will be there first, followed by the argument that's passed in. We can actually do this with multiple arrays as well. So we could do something like 2, 3, 4, 5. All right, so we could pass multiple arguments in. All of those arrays get merged in, get appended to the very end. Another way we could do it is using our spread operator. Right? If I did something like dot 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 left, dot 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 right within an array, that spreads those apart and creates a new array with those values inside. So either one of those will work. What do you all like better? What do you think is clear? Do you think concat is clearer, or do you think using the spread operator is clearer? Which ones do you all like? Sorry, it's going for spread. I don't like it. I think it looks cool to me, this option. What do the rest of y'all think? Anyone else disagree here? Man, everyone agrees. Spread's better. I love freaking cat. It's so old. It's just the old way of doing stuff. Lame, boring. All right, let's go ahead and use the spread operator. So once one half is empty, we're going to append the remaining elements of the other half to the merged list. So we could do something like const result equals. First of all, we need to include those merged elements, right? That's our sorted portion. And then we can go ahead and add and spread whatever's remaining in the left and right side. We've gotten to this point, consider our while loop here. We've gotten to this point, that means one of these is empty. But if you spread an empty array, nothing gets added. So it doesn't matter necessarily what order you put these two in. So we'll merge all of this together. All right. Last step, we got to return merge list. Let's go ahead and try this out and see if it works. Whew, not bad. Not bad at all. We add a few more items in here. Say do that. Say that. Looking spicy. Looking nice. Excellent. All right, so let me clear out these comments, which I think is making it a little bit harder to read here, so we can just look at the basic code. All right, and that's it. We don't even actually really need this. We can just return this at this step. So we create our empty list. We loop through as long as either of these arrays have any items in it. We check and compare the first elements of each array. Depending on which one's less, we push that value into the merged array and remove it from the left or right array. Not bad. Last step here. So we have our merge function. Our last step here is to do our merge sort function. So I'm going to give you a little bit of time to do this. We're running okay on time. So I'm going to say merge sort. We'll pass in the entire array. And we want to do this. If the list has one item or is empty, return the list as already sorted. Remember, that's our base case. Otherwise, we're going to divide the list into two halves. Already discussed some ways to do that, right? With the left half, we're going to recall merge sort. With the right half, we're going to recall merge sort. And then we'll return the merged version of the left half and the right half. So that is the plan for merge sort. So down here, I can update sort of my test case by just changing this into one array. And what we're expecting to get out of this at the very end is 2, 3, 4, 5, 7, 8, 9. All right, so you have your merge function. Let's go ahead and we'll take, I'm going to say 8 or 9 minutes or so to finish up merge sort. All right, good luck. Get to it. Hopefully you got to a good spot with that. Let's go ahead and work through it together. We just got 30 minutes left in the class. I want to give you all a little break before we can do the lab so we can relax our brains for a moment. All right, so following our pseudocode, let's go ahead and build it out. So the first step is if the list has one item or is empty, so we could do something like if array.length is less than or equal to 1. Then we want to go ahead and return the list as it is already sorted. All right, so not bad. Otherwise, we're going to go ahead and do the following. First, we're going to divide the list into two halves. So we saw how we could do that, right? We can grab mid right up here. We see mass.floor array length divided by 2. Array.length divided by 2. And we also saw how we can split the array into two different halves using that value. So we could do something like this. We have the left side, we have the right side, and we're using mid to calculate that. Next, we're going to go ahead and, how do I want to say this? We're going to call merge sort again and assign it equal to some new variable. And we're going to call merge sort again on the right half as well. We can actually, I think, do this without even assigning new variables. So we could do something like return merge, merge sort left, and merge sort right. So this will allow us to merge together the result of merge sorting left and merge sorting right. That process is going to cut everything down to little halves until we hit this base case, in which case once this merge function has the results of merge sort on the left and right half, it'll go ahead and merge those two small arrays and continue on and on. Let's go ahead and run that, see what happens. It's pretty cool. Yeah, I think it's cool. I think it's kind of cool. I don't know. Maybe I'm just a nerd about this stuff, but it's kind of neat. This is actually not that much code to do something that I think is pretty complex. So when we look at our merge sort function, I can remove these comments just so it's easier to see. This is not that much code, right? So here's our base case. We have a chunk of it where we split the array into two halves. And then we merge them. It's really just kind of those three steps. And our merge is also, I think, pretty straightforward. We're again assuming sorted left and right sides. And then we're just checking the first element of each, adding it to our new array. That's it. Any questions on this code? Going good? Everyone seemed sad and confused before. How about now? Are we sad, confused, and a little excited? Maybe a little inspired? I don't disagree. I just was hoping this would be a moment of joy in our sad and confused lives. All right, Omar says slightly less sad and confused. I think that's a good goal. I think that's a good goal to go for. Slightly less is pretty nice. Pretty nice. All right, excellent, y'all. I hope in terms of the recursive aspects of this, that's it's making some sense, as well as some of the steps that we followed in terms of these two different little functions to build merge sort. Each one on its own, I think, is pretty understandable. Let me find, I have another one of these examples where it's very verbose with a lot of output. And so I just wanted to share that so we can kind of look at it and kind of see it happening in action. I'm going to go ahead and comment this stuff out just for now. I'll paste this down below. So this is the same code. I've just added a bunch of console logs and statements to try and improve the output here so we can see it. So let's take a look. Doodly doodly, look at all these steps. So just so we can walk through and see. So here's the array that we're starting with. This is all the numbers from 0 to 9. And then we see these steps where it's merging, 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 right, and calling merge sort on, first of all, this left-hand side, right? So this left-hand side is 59018. We call merge sort again on it. Then we're just looking at 5, 9, and then we're looking at just 5 and 9. So that's our breakdown that we can see, right? We then call merge sort again on 5. We hit the base case. We then call merge sort on just 9. We hit the base case. And then we come back and we start merging 5 and 9, these small arrays. So we compare left and right side. 5 is less than 9. So the result of that is our new array just has 9 in it. This is the new array. The left side has nothing in it. The right side has 9. And so we go ahead and add everything uh, together. So we add right to the very end. That gives us the result of 5 and 9. We then do that same process with the right side. And we can see here we have 0, 1, 8. We then split again, merging 0, 1, 8. Merge sort at 0 is good. This is a case where the array is a little bit uneven in size. So for 0, it's already been completed. That's our base case. And then for 1 and 8, we have to split once more until we get to 1 and 8. We then follow that same sorting process, 1 and 8. And then we jump back up, and now we're merging 0 and 1, 0 and 1 and 8. Here we can see, first of all, 0 is less than 1. That's the result. Everything is gone from the left array, and so we just tack the entire right array onto that final result. And that's our result here. Now those two subarrays, we're going to merge back up. That's 5 and 9 and 0, 1, 8. And here we can see the real meat of the process, right? So we compare the first values here. 0 is less than 5. That goes into our new array. 1 is less than 5. That goes into our new array. 5 is less than 8. That goes into our new array. 8 is less than 9. That goes into our new array. We just have one item left in the left side. We tack that onto the end. And that's our result. So the entire left side of this gets sorted before we even begin on the right side. And that makes sense. When we look at our code, and I'll scroll up to the comments out version here. It's a little easier. When we look at our code, this is the first thing that happens, right? So we're doing all of that first and then bringing it back up when it gets evaluated. It's the entire left side first. Same thing happens with the right side. You can see multiple steps here. We're comparing the two subarrays, sorting those, comparing these other small subarrays, comparing them together. And we get back to this step where the left and the right side are sorted and we're just merging together. So here we can see we're comparing all these different values and slowly building up our new array. The most complicated part of the merge right here. We end up with two values left in the left array, and those get tacked onto the end, leading to a totally sorted array. So again, how we can think of it is we're splitting all the way down, performing all the merges, it comes back up. That is how it's working in the algorithm. It's traveling down the left side first, if that helps in terms of how to think about this. All right, lots of talking. Let's go ahead and move on to our break. I know it's a little late here. We're almost out. I apologize. Just a lot of content to go through. We'll take 10 minutes. I think we'll still be fine to end on time here, and then we'll go over to the lab. I'll go ahead and introduce it. There's a solution in the code, so we can get it started, and then we can close out. I think you'll all be fine finishing it out on your own if you're able to get through that first part. So I'll see you all in 10 minutes. Back. We're basically at the end of our lesson here. So let me just go ahead and walk through the lab for you all. All right, so what we're looking at, just like the other examples here, right, we have a little bit more complex of a data structure to work with, a bit more of a real situation. So we want you all to implement merge sort using this library data. The idea is that you're going to sort all of these books by the ISBN code right here. These numbers can get compared with one another, even though they are strings. JavaScript will do that for you, which is quite nice, I believe. So you can go ahead and try that out. In terms of completing this, it should be very similar to what we just completed. However, you're just going to have to think about, how do I access this value out of there? Is there any other additional work I need to do to make sure that those are sorted? So without any further ado, let me go ahead and I'll put 6 or 7 minutes on the clock just for you all to do this. I would definitely encourage you to look back at the merge sort that we just went through. It's going to be very similar. And then once we come back, I'll talk through some of the differences in the solution in this file, and then we'll close out for the day. All right, so good luck. I'll put 7 minutes on here. And we'll go ahead and get started. Let's go ahead and take a look. You get to a solution already? I think we should just be able to basically pull over the code we had here. Oh gosh, sorry y'all. My dog has something to say. Let's find this. I think we basically plug that in. There really should be minimal differences here, right? The only difference I think we're looking at is this comparison, where we'll need to make sure to grab the ISBN number. Everything else in terms of the array, the values that are getting pushed around, things like that, I think should probably just be able to stay the same. Let's take a look. Oh, it's because I didn't change some names and I didn't change everything. Let's try that. Get rid of that. All right, I think we're looking at, oh, does it just look exactly the same? Are these already sorted? No, no way. Oh, what did I forget here? Well, did any of you all get a solve here? Nah. So I think we should be seeing, let's compare some of these values. Is this less than equal to? Yeah, so I would think this would pop up first. Oh. Well, by the way, we have a solution over here, and I can take a look at that with you all. And I'm sure there's just something here I'm not seeing. So we look at the solution over here. See that a lot of this does remain the same. So we have math.floor, library array.length. Oops, sorry about that. We have our guard clause up here, or rather our base case. We're getting the middle point. We're then calling merge sort on the left half and the right half. And then we merge that sorted left half and the sorted right half. The differences start right around here. So with merge, the difference that they've made in this solution is to, instead of popping from the array, to use indexes. And this is a pretty common pattern that I think you all might see as well. So with this, we'll see something like left index, right index. And as we work our way through the array, we'll go ahead and compare the values overall. So the left index will get moved up whenever the left index ISBN is less than. So we're going to kind of move up and no longer include the value that we've just pushed into the sorted array. And same thing with the right index. So just a slightly different way to sort these values. Let's go ahead and copy this over. And perhaps there's something interesting in this that, oh my gosh, here we go. That will be a little bit different. Does it have everything? It does. Okay. All right, there we go. So in this case, we can see it does indeed sort. Looks like it's sorting the exact opposite direction. Right, so it starts with D, C, B, and A. What's the difference here? Left index less than. What did I have over here? I don't know, y'all. Looks pretty good to me. I'll play around with it and see what maybe I've missed in our little solution here, but it does look like this one works. Either way, we're doing kind of the same thing here. And you can see that we have just a slightly different version of this merge value. I think that is it. We're at 12:30. So just to recap quickly here, I know it was a long lesson today, a lot of different ideas. We talked about merge sort today. We talked about the big O efficiency measurement of it. So that was n log n, right? It's a little bit more efficient than some of the other sorting mechanisms that we've gone through. We talked about how to build up the merge sort function with a supplemental merge function, right? That's going to take two sorted arrays and merge those ones together. We're able to build that out in pseudocode and then build it out in code as well. That's the end of today's lesson. The next one we'll go over Quicksort, which will be the last sorting algorithm we will cover before we dive into some more programmer specific, I should say, parts of our curriculum. That's it. It's good seeing you all.